So now that we've walked through the EX36 driver program, let's go ahead and take a look at the results of running this program to see how the different collectors perform with sequential and parallel processing. And then we'll also take a look at the concurrent set collector implementation to kind of round things off and wrap things up. So we ran the test program. Keep in mind, of course, that when we run the test program in this context, I'm running Zoom. So there's probably one, maybe two less cores that are available for running the test, but this is pretty representative of what you would get if you ran this with all the cores available. So we start out by doing the HashSet test for 1,000 words, and you can see that we get the following results. You'll notice that for a small n, only 1,000 words of Shakespeare, we have the sequential stream implementations actually performing the best. And that should match our intuition at this point. When n is small, parallel streams doesn't really buy you anything. So I would almost just ignore these results because they're not particularly meaningful for the purposes we're doing. You'll notice when we go and do for 10,000 words, the sequential versions are still outperforming the parallel versions. Okay, so we'll continue to ignore that. Now we get to 100,000 words. Now, where n has gotten bigger, the parallel versions are starting to dominate because we're actually getting a win from doing parallel processing. But you'll notice for 100,000 words, the parallel non-concurrent version is working best. But when we get to all the words in Shakespeare, and there's approximately 910,000 words in Shakespeare, give or take a few, now we get the results that I would expect as n gets large. The parallel versions both perform better than the sequential versions by quite an enormous amount. And the parallel concurrent collector is now outperforming the parallel non-concurrent collector. And so what you're seeing there is that as n gets bigger and bigger, we get a bigger win for parallel processing, no real surprise. And as n gets bigger, we're getting a win from not having to merge the intermediate sets together in order to get the final set. And you'll notice, by the way, this is for hash sets, not for tree sets. So this is the performance for hash sets. Now let's take a look at the performance for tree sets, which, remember, are implemented as essentially balanced binary trees. Once again, for a small number of n, sequential beats parallel. As we get a little bit bigger, and for tree sets, parallel concurrent is starting to win, but not by very much. It's probably in the noise. As we get to 100,000 words, then the parallel concurrent is outperforming everybody. So it's a little bit better than the hash set implementation. And then when we get to all the words in Shakespeare, now we have what we would expect as n gets large. Parallel concurrent tree set is quite outperforming everybody else by a non-trivial amount. And in fact, it's substantially faster than the sequential versions, both concurrent and non-concurrent. So really quite interesting results. The other thing I'll show you, just because it's kind of fun and as a trivia question, if anybody asks you how many unique words are there in Shakespeare, you can tell them that it's on the order of 23,514. So the reason why we know this is because both versions of this collector test benchmarking and case study are using sets to represent the results of doing the collection. And of course, there's no duplicates in a set. So these are all the words, these are all the unique words in Shakespeare. Some of them, of course, are people's names, but I think it's just kind of fun to see what words show up. I have another program that counts the number of times different words show up in the works of Shakespeare. And as you might expect, very somewhat archaic words like the, Thee, or Lord shows up all over the place there. All right, so hopefully that helps you get a good feeling for why we get a win when we're using parallel streams as n gets big, and also why we get a win when we use parallel collectors or concurrent collectors. The last thing I want to talk about here is the concurrent set collector. So let's go ahead and take a look at concurrent set collector. This is a generic collector, you could use this for pretty much anything, that accumulates the input elements of type E, which is the first parameter, into a concurrent hash map key set view, which is essentially a concurrent hash set. And then it returns a type S that extends set. So we parameterize ConcurrentSetCollector with the element and the type of set, and then we use those parameters to create the generic parameter arguments to collector, which is the interface. So it's a collector for a stream of E that has a mutable result container of type set of E, and it returns a return type of S. All right, so let's take a look and see how this works. This is really, really cool. So we're going to keep our own set supplier as a field, and you'll see why we need that in a second. Our constructor for ConcurrentSetCollector goes ahead and stores the parameter that's passed to it into the set supplier field, the mset supplier field here. The supplier, which is a factor method, returns concurrent hash map new key set. And concurrent hash map new key set is this method, which is essentially a virtual constructor that makes a new instance of something called a key set view. And you can see that the key set view is basically just a wrapper around a concurrent hash map where the key is the set key, and then it's just got a Boolean as the second parameter. It's really not used. It's just set to true. And so key set view is this little helper class that uses concurrent hash map to implement a set. So it gets rid of the value part and just focuses on the key part of this. Okay, so that's what the supplier returns. The accumulator returns a set add method, which of course will actually under the hood be the concurrent hash maps set method. So it'll be properly synchronized. And then down here we have a combiner. Now, a couple things to note. The combiner, when we use this with a parallel stream, will not be used. If we use this with a non-parallel stream, a sequential stream, then the combiner will be used. And what it does is it's clever, and it looks to see whether the first set is bigger than the second set. And if it is, it adds the second set to the first set. And if it's not, it adds the first set to the second set. And that's because it's cheaper to merge the elements from a smaller set into a bigger set than the other way around. Keep in mind that the combiner is not used for parallel streams. And then finally, we have the finisher. Now, this is a really good example where it pays off to do something interesting and different with finisher. So what we're going to do here is we're going to come into the finisher, and we're going to take the mutable result container, which in this case is going to be a concurrent hash maps key set view, so a concurrent hash set, if you will. And we're going to make ourselves a new empty key set, I should call this set, that's empty. And then we're going to use this to find out what the actual type was of the parameter that we're using to instantiate the set. So if the new set is a concurrent hash map key set view, we're done. We're just going to take the set that we've been collecting into, which in this case is a concurrent hash set, and we're going to return that as the result from finisher. So we don't have to do any other copying or merging or anything. So in the case where we're using this with the concurrent hash set variant or the hash set variant, no copying is required. However, if we were collecting things into a tree set, then what we're going to have to do is we're going to have to take the contents of our concurrent hash set and then add it to the empty concurrent tree set or non-concurrent tree set. So we're going to have to add the contents there and then return that. So this is just a little optimization we put in there to make things work faster if we have a concurrent hash map than when we're using a tree set. So that essentially illustrates how you can do this particular case study. I think it's a very cool mechanism and helps to demonstrate the power of both parallel streams as n gets large and concurrent collectors as n gets large.